Let us summarize what we have done till now. So we were looking at Kepler problem, where the potential energy of the system is given by minus k over r, okay, and we had reduced the, of course we were doing two-body problem, and then we chose this potential, and we found that the r is given by the following relation, which are basically conic sections, and you have here L square over k mu. K and mu both are in the denominator of L square, and then you have 1 plus epsilon cos of theta. Okay, so that's what we had found. I have here on the right hand side the graph of U effective, okay, with versus R. Okay, and we have already discussed that the solutions which we have found, which is given here, okay, they provide the following orbits for the problem. So if you are here, let me try to choose a different color. If you are at this value of energy, that is the minimum, then only one radius is possible, which is this, okay, and you have a circular orbit. So let me, your E minimum, and you get a circle, okay, circular orbit. Then if you are anywhere between this energy, minimum energy, which is a negative value, and 0, then you get an ellipse. So if you are anywhere between this point and that point in energy, then you get an ellipse. Okay, so if you are here, you get, if energy value is this, then you get an ellipse. Okay, if your E is equal to 0, let me write it here like this. And recall, if energy is 0, then you get a parabola. Okay, so for this you get a parabola. You see, it comes here and then it returns and goes towards infinity and never comes back. So this leads to a parabola. And if your energy is higher than 0, if you are anywhere here or wherever you are, that is also an open orbit. Not just open, it goes to infinity, the particle returns to infinity, and it is a hyperbola. Okay, so that's what we had found. Okay, now let's think about what are the questions that we would like to ask, given that we know this much. Okay, so I would encourage you to take a moment, maybe stop the video, and think about things which you would like to ask further in this problem, given that you have found that the orbits are parabolic. What are the questions that are coming to mind, and let's list them. Okay, so you may stop it for a moment and return after you have spent some time thinking about the questions you would like to ask. Okay, so hopefully you have returned with a list of questions, and I will write down a small list which typically we can ask right now. So you may be interested in asking, for example, question number 1 could be, yeah, So your first question could be, what is the smallest value of r that can be achieved? Okay. Equivalently, what is the closest, what is the shortest distance between the particles m1 and m2 that you are going to see in this system? Okay. So that is question number 1. So let me write it down. What is the smallest value r can take? So that's a nice question to ask, because you would of course like to know how close these two particles are going to come, right? Then you may ask, what is the largest value that r can take? How much, what is the maximum separation between them that's going to be possible? So what is the largest value that r takes? Okay. Now you may also wish to think, what distinguishes two elliptic orbits of same eccentricity? Okay. Of course you will think of the scale. One could be smaller, another could be larger. They may have same eccentricity, but what is controlling them? Okay. So we'll make this question a little bit more precise later, but for the now we will leave it a little vague, but nevertheless I'll write it. What distinguishes two elliptic orbits of same eccentricity? Okay, we'll make this question more precise after some time. Maybe I can say a few words to the students who are listening to this video. Okay, and if there are some faculty who are taking it for FDP, they may ignore whatever I am saying and excuse me, because I would like to address the younger lot, the students, for a while. Okay, so please excuse me. There's one experiment that I sometimes do once in a given course, and that is the following. So usually after I have spent some weeks and I feel that students are getting along, I would typically I will choose one day on which I will decide that I will ask the students to, leave aside their notebooks and close their eyes and put their head on desk and try to think of questions that they would like to ask, okay, in the connection of whatever we are studying on that day. Okay, and I will usually give them 5 to 7 minutes to think. So they are not allowed to write anything, they are not allowed to talk, they just have to think. And after those 7 minutes, they will be allowed to write it on a piece of paper, which they will either read out in the class or they will hand it over to me. Okay, and I have found that students find this interesting, because usually they don't get that much opportunity to ask to themselves the questions the questions they may be interested in at that moment about the subject they are learning. Okay, so if you are a student who is taking this course, I would definitely encourage that you sometimes just leave the book, leave the notes, and think of things which you would like to ask. Okay, for example, here you might have come up with these questions, the simplest ones or even better ones, when a few minutes ago I asked you to think of some questions. Okay, anyhow, so let's proceed further. Yeah, so let's try to answer these questions which you have written down. Okay. Let's go to the next sheet. Here. So that is our orbit. The origin is here, and my question is r is equal to L square over k mu 1 plus epsilon cos of theta. Okay, and theta is measured with respect to this line. So let's say theta is pi by 2. Let's see what is that. When theta is pi by 2, cos theta is 0, and you are left with the 1 in the denominator, and your r is L square over k mu, okay? Which means this distance from here to here, which I will call rho, okay? That is what you get for pi by 2, which means rho is L square over k mu. Okay, so I will then rewrite this equation, equation of orbit as rho over 1 plus epsilon cos of theta. Okay, that's fine. Later we'll see that this is not still the best thing to write, but anyway, it tells you what the numerator is in terms of this figure. Okay, but this is still not the best way of writing the equation. Anyway, so let's ask about r minimum. Well, that r minimum occurs when theta is 0, because when theta is 0, it's going to be here. Okay, and we have already seen that our curve is like this. Okay, it's not that way. So your r minimum gives you r minimum you get by putting theta to be 0. When you put theta to be 0 here, it is rho over 1 plus epsilon. Okay, so you get for theta equals to 0, and your r minimum is rho over 1 plus epsilon. Okay, that's nice. Maximum value of r is taken when theta is pi. So from here you go to there, okay, this angle. So when theta is pi, you are here, and r maximum is when theta is pi, cos theta is minus 1, and you get rho over 1 minus epsilon. Okay, so that's nice. So here it is r minimum, that is r maximum. So r maximum is from here to there. Okay, this is r minimum from this point to the origin, and clearly this entire distance from minimum to maximum is somewhere in the center of this ellipse. This is the center of the ellipse. Okay, and the distance from the center to one end is what you call semi-major axis, and similarly on that side you call semi-minor axis. So the full distance from here to there is r max plus r minimum. Let me not write it, it's cluttering. Okay, so this is major axis, this length, and half of it would be semi-major axis. So my semi-major axis is how much? Is r max plus r minimum divided by 2, because then I count from here. So I have r minimum plus r maximum the whole thing divided by 2. Okay, and what is that? It is rho over 1 plus epsilon plus rho over 1 minus epsilon, which is rho epsilon will, okay, 1 plus epsilon plus 1 minus epsilon will give you a 2. Okay, and there's a factor of half which I have missed. So you have rho over 2, but when they go up in the numerator, they bring a factor of 2, which will cancel the half here, this 2 in the denominator, and you get rho over 1 minus epsilon square. Okay, that's your semi major axis. Let's check whether it's correct. Okay, yeah, that's correct. Now how can I find out the semi minor axis, meaning this distance? Let me give semi major axis a name. I'll call it A. A. And let's call this one B, semi minor axis. So B is defined to be semi minor axis. And how can I find it out? Well, you can find it out by recalling what the definition of eccentricity is. Okay, do you recall that? So if you recall, your epsilon is defined by 1 minus minor axis or semi minor axis. It does not matter because there is just a factor of 2 divided by major axis. If you take semi minor and semi major, the factor of 2 will cancel in the numerator and the denominator, so it does not really matter. Okay, that's the definition of eccentricity. So I can use this epsilon to write that semi minor axis is 1 minus epsilon square in the square root times semi major axis, which I am calling now as A. So let me put the A here. Okay, so my B is A times 1 minus epsilon square. Okay, that is good, and that is also good. Okay, so let me just write it down neatly here again. My let me write it down like this. From here to there is A, and this is B, from here to there. Okay, now before I leave, for easy reference, I will write here that A is rho over 1 minus epsilon square, and B is A times 1 minus epsilon square. Okay, let's leave it like this. I'll give you 2 very small exercises to yeah, very simple. So exercise. Please check that 1 minus epsilon square is minus how should I put it? Yeah, minus 2 over mu k square L square times E. Let's see whether at least the sign part is okay. Our epsilon is less than 1 because it's an ellipse, so epsilon square will also be less than 1, which means 1 minus epsilon square would be positive. On the right hand side, even though you have negative sign, but remember E is negative, which makes the entire thing positive. So this looks fine as far as sign is concerned. Okay, let me put epsilon is less than 0 because it's an ellipse. Second exercise, please check that the semi-major axis, which we denote by A, which is our rho over 1 minus epsilon square, is minus k over 2e. Okay, again E is negative, so minus k over 2 is a positive quantity, which is good because we need A to be positive. It's a length. Okay, also note that the length of semi-major axis does not depend on L. Okay, meaning when you fire the particle mu, the reduced particle with reduced mass mu, the energy of it or the velocity of it is going to determine what the semi-major axis would be, what will be the length on along the theta equal to 0 direction. Okay, from minus pi to 0. That length of semi-major axis is completely determined by the energy you give. Okay, and angular momentum has no role in determining that. So let me write it down. A is a function of E only. Okay, I'm not saying anything about K because that's given by the problem. Okay, that is not determined by the initial conditions, or okay, that's given by the problem. Another exercise, let's find out what the semi-minor axis is in terms of the parameters which you control, which is the angular momentum and energy, and it turns out to be the following. It is minus 1 over 2 mu E, and that sits in the square root, and you have a L here. Okay, minus sign is fine because you have energy here, which makes positive. Okay, that is nice. And okay, let's do a quick test to see if these results which I am giving you are at some level okay. Okay, let's do that test. So I'm not going to worry about the factors of L and mu, but I'll do some checks to see whether these are okay or not. Okay, so let's look at let me call it a test. I'm testing it. So let's look at B over A. Remember, B over A is related to eccentricity. Okay, let's go back here. Remember, epsilon is minor axis or major axis. So I just want to calculate B over A from okay, that is perfect. I think yes, that's good. So let me calculate B over A and let's see what it is. So B over A will be proportional to, where is B? B is this. So it brings L over square root of E. So L over square root of, let me write mod of E right now instead of carrying out minus sign. And then I have to divide by A. And what is A? A goes as 1 over E. 1 over modulus of E. Okay, that's how it goes. Which is L times square root of modulus of E. That's what B and A are giving. And if I have not made a calculation mistake, then as far as L and E dependence is concerned in here, okay, it should be the same as you should get in 1 minus epsilon square, right? So let's see what our 1 minus epsilon square is. My 1 minus epsilon square is a function of L modulus of E in the square root, this thing squared, but anyway, this is a function of this. Okay, so which means that my B over A is coming out to be consistent with what I expected of the eccentricity. Okay, and so this is these are the kind of small tests we should keep doing during calculations to be sure that we are not making some mistakes. Okay, that's fine. Now let's ask the following. Let's go back to our third question. What distinguishes two elliptic orbits of same eccentricity? So what I'm really trying to say, ask is the following. Let's say I have fired my particle mu with some energy and some angular momentum, okay, and I get some orbit of some ellipticity epsilon. Now what I want to do is, again repeat the same thing. I want to fire my particle mu with a different energy, and of course I should fire with a different angular momentum such that I get the same eccentricity. Okay, so I want the same eccentricity as before, but I want to have a different energy. Okay, then how should my angular momentum be related? That is what I want to ask. Okay, so let me write, or so what I want to write is, yeah, so what I basically want is orbits of same eccentricity but different size. That's what basically I'm asking. You see, if you draw an ellipse on a sheet of paper, okay, and you photocopy it and zoom it by 2 times or 10 times or whatever, the eccentricity is same for all these copies. The basic ellipse is still the same. What is different between all these copies is the scale. Okay, and that is what I mean here, that I keep the epsilon same, and but the orbits are of different size, okay, or equivalently different scale. So very naively I would think that because my r is given by the following, remember I wrote r as rho over 1 plus epsilon cos of theta. You might think that rho is the scale because epsilon remains unchanged, and rho is the one which will determine the scale, okay, and where rho is given by L square over k mu. Okay, that is the naive expectation if we are not being very careful. So naively, scale is controlled by, or not just say scaling is rho, scale factor is rho. But this is not correct. Okay, this naive expectation is obviously not correct, because I should ensure that if there are any factors of a over b which are in rho, I should factor them out. Okay, otherwise I'll be putting in unnecessary. See, if I divide by this thing by epsilon, okay, then the scaling factor changes, right? So we have to be careful in what we are doing. So let's put it in the right form. Let me write not correct. And so I should recall that my rho is 1 minus epsilon square times the semi-major axis. Okay, let's go back and check whether we have encountered this before. Yes, indeed. So your rho here is 1 minus epsilon square times a. I should substitute that here. Now you see, I have pulled out of rho a factor which does not change when you scale up the ellipse, because the epsilon is not going to change, right? And that is what I was saying, what is wrong in our naive expectation. So my my r is a times 1 minus epsilon square over 1 plus epsilon cos of theta. So scaling is determined by the major axis, semi-major axis, let's say, is determined by semi major axis. Okay. Okay, now let's ask, what should we ask? Let's ask, if you want to keep epsilon unchanged but scale up the ellipse by a factor of 2, how should you change your E and L? After all, they are all determined in terms of E and L. Okay, the energy and angular momentum is all you have in your hands. Okay, so if I want to scale it up by a factor of 2, what should you do? So here, question. Let me. If we want to keep epsilon unchanged, okay, but scale up the ellipse by a factor of 2, how should my E and L scale? How should E and L scale? Okay, let me go back and try to say what I really mean by this question. Where was it? Somewhere here. Here. Okay, let's say you fired a particle from here, some distance away, with some energy E, and you fired at some angle so that it has angular momentum L, and you get an ellipse. Okay, you got an ellipse of some eccentricity epsilon. Now you take that ellipse and just photocopy it with a zoom of 2. Now you get another ellipse, okay, with a scale factor 2. What we are asking is, to get that new ellipse, what should be the energy with which I should fire, and what should be the angular momentum? Okay, that's what we are asking. Okay, so clearly, because my epsilon is going to be unchanged, it means that the ratio of semi-major axis and semi-minor axis is going to be unchanged. Okay, so epsilon unchanged implies my B over A to be unchanged. Okay, now B over A, you can quickly see that goes as L times square root of E. Okay, if you divide B over A, that's what you get. Now let's say I take energy and scale it up by a factor of nu. So I make E to be nu times E. Then if I take my angular momentum and scale it as 1 over square root of nu, so I reduce it by a factor of 1 over square root of nu times the original L. If I do this, then my B over A does not change. Unchanged. Right, that's correct. So L goes as nu square. Sorry, what have I done? Yeah, E goes as nu, so you get a square root of E here, square root of nu times E here. Let me write it anyway. So L times square root of E goes as L becomes 1 over nu L, and E becomes square root of nu E, and these two cancel. Okay, so you get the same thing back. So that is correct. That is correct. Very good. Now what? Yeah, that's correct. Okay. Now I wanted to ask, what I would like to know now is, given this situation where I have scaled the energies E and L by these factors, what is the new semi-major axis? Because that is what is going to determine the scale of the ellipse, right? You remember this? Let's see. somewhere here. Yeah, here you have A. Okay, so if I know how A has changed, I will know the answer. And let's go back and see what is A. A goes as 1 over E. Okay, so my A goes as, or is proportional to 1 over modulus of E. That's what we saw just now. To be sure, let's check once again. Yes, correct. A goes as 1 over mod of E, which means under the scaling I have done, my this will become nu times. Okay, so it will get scaled by a factor of 1 over nu. Okay, that is looking fine to me. The size of mine by A, so it goes by a factor of nu. I think I wrote wrongly in my note, so this is correct here. Okay, so that is how it happens. And let me also throw in a bit of nomenclature. These R minimum and R maximum, they are called our apsidal distances. Let me draw this. So this point and that point, they are called apsidal distances. Okay, we'll continue and talk more about center force problem in the next lecture. Okay, so see you then next.